Hello all. So today we will be solving this problem from TIFR. Uh, this problem actually requires some simple computations in the field of linear algebra. Okay, so we will see it step by step and how to do it. So first I will give you the answer and then I will show you that how to get to that answer. Okay, there are very simple computations that you uh, so I will leave for you to do. And yeah, so let's see how to solve this. So first thing is that so it's no, it's not true. So one of the very basic example that you can actually take from here is that if you take this matrix, and this matrix will work anywhere. So since it's given to be a complex matrix, just take this 2 cross 2 matrix. Okay, so why we are able to do it? See, the thing that has been mentioned here is this, that what are the properties of E? The properties of E are these. First, this is in M2C. Hence, you know that every polynomial is factorizable, basically. This is the first property. The second property is it is invertible, which reduces the class of matrices quite a lot. It is given to you as diagonalizable. Okay, so suppose, let's say, and the most important property of A that is given in the hypothesis is that A and A square, they both have the same characteristic polynomial. All right, so what does that mean? So from here, what you can actually understand is that since it is given to be a diagonalizable matrix, so suppose irrespective of repetition of eigenvalues, suppose lambda 1, lambda 2 are eigenvalues of E. So then the eigenvalues of A square are lambda 1 square and lambda 2 square. This is period. This is something that we can actually solve. Since it is given to be a diagonalizable matrix, then you can actually directly solve it. But anyways, if lambda is an eigenvalue of A, lambda square is an eigenvalue of A square. So but here, since it's given to be diagonalizable, this will be the exact eigenvalue set. And since it's also with the same characteristic polynomial, so what does it mean? That they have the same characteristic polynomial. So whenever, so what is the characteristic polynomial of E? The characteristic polynomial of E is this. Okay, so this is same as the characteristic polynomial of A square. Let's just take it mu. All right, so the moment you have this, all right, so it implies that since E belongs to M to C, all the roots of characteristic polynomial of E and characteristic polynomial of A square are same, right? This is what we get, because and the moment you have all the roots are same up to permutation, of course. I mean, up to permutation means like if you have let's say x minus a into x minus b as characteristic polynomial of a, then characteristic polynomial of a square might be x minus b into x minus a. Okay, and there will always be a factorization since we have it in C, it's complex entries. So now the moment you get this, then if you look at the choice of our elements of A, so if you take A square, then A square is nothing but omega square omega, and hence it has the exact same characteristic polynomial as A, right? So this is where this I mean up to permutation we are talking about. Since it's all commutative, we don't have to worry about it. Okay, so thus you get a matrix. So thus A is a matrix which is not identity but has all the other properties. Okay, so what are the important observations that we made? Since it's 2 cross 2, you can just do it. So the roots will be always equal. Okay, so I mean, as you can see, the choice of our matrix, that means the roots of characteristic polynomial of A are omega omega square. So if you the choice of roots are omega square omega for A square. So this is the basic thing that we had to do. And once you understand that the roots are equal in both these levels, then you just put them in the diagonals. Okay, so this is all. Thank you for joining. We will meet with another problem from TIFR in next session. Okay, so the final answer to this question is false. So this is false. And the counter example is this. Thank you for joining.